www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Good morning. So let's get started. Today we'll be talking about Fermi Dirac Statistics, that is lecture 9. And what statistics has to do with the discussion that we had previously is the following. This is the analogy and sort of where you are in the course. You remember that the main purpose that we are going through all sorts of complicated things, calculations and differential equations, Schrodinger equation and all sorts of things, is because we want to calculate the number of places the electron can sit. All electrons, although they are the same in vacuum inside the solid, they have to stay in different bands. Different bands have different effective masses, right? Density of state, and therefore they move with various properties, with different properties, and therefore they are not all the same inside the solid. So far, that's what we have calculated, where the electrons can sit. If it were a high-rise apartment building, in analogy, you would say we have calculated how many apartments there are where the occupants can stay, but the tenants can stay. But how many tenants do I have, or where they actually sit? You see, that is the discussion for today's lecture. Now, one thing you could immediately understand that there is a puzzle here, because assume that you have 250 electrons, for example, and you have 10 bands. Now, in principle, if you didn't know anything else, then you could say, well, 25 of them would sit in each of the band. You see, 10 bands, 250 electrons. And in that case, all the bands are partially empty or partially full, as you say it. And therefore, all 10 bands should contribute in energy. Or somebody else could say, well, no, just the first 2 bands takes care of, the 250 electrons, and the remaining 8 are empty. How do you know where they sit? And that is the purpose. Specifying that distribution is the purpose of today's lecture. Now, what I'll be doing is explaining that there are some rules for filling these electronic states by electrons. Now, of course, that rules tells you what distribution is most probable. And we'll do that. The next one will be a Fermi Dirac Statistics. We'll try to derive it, but we'll derive it in 3 techniques. The first one is based on what you have in the textbook, just for the sake of continuity. The other 2 will be simpler derivation that we will be able to use it in more complex situation that will come down the road. But all 3 are exactly has the equivalent information. Ease of use is slightly different. And finally, by using this Fermi Dirac statistics and the density of state, solution of the Schrodinger equation, we'll be able to calculate the number of electrons in an intrinsic semiconductor. And that is at least finally we are getting to get that carrier density. Remember, that's what we are after, so that we can apply an electric field and see how much current flows. So that's where we are going. Now, if you remember the EK diagram, perhaps you remember that this is a diagram from one-dimensional solid, a set of n atoms. And if the spacing is A, then the Brillouin zone is pi over A to minus pi over A. Electrons sit in individual bands, and these bands each has n state, n number of atoms, n state, twice n state if you include the spin. So each band actually has always even number of states, right? 25 atoms per band, you always will have 25 states. If you include spin, 50 states. Each one of these bands will have that. Now we said that we don't want to carry around all this complicated information, but rather we want to encapsulate them into simple things like density of states, because the electrons actually might sit on the bottom or top of each band. So we looked at the density of state. And the red one you can see associated with the red band, and the blue one is like a valence electron-like band, concave downward. And let's focus on one, because if we know how to take care of one, we know how to take care of all of them. Do you remember that in the last class, I derived this density of state, this formula for density of state, how many per unit energy and per unit length or per unit volume, right? This is within a unit box of material, how many states I have. Now, very quickly, you notice that there is a discrepancy, because on the right-hand side, the formula I have written is for three-dimensional solid. Do you remember square root of E for 3D? 1D, it was 1 over square root of E. And in 2D, what was it? It's a constant. So here you see I haven't drawn very carefully. On the left-hand side, I have done the one-dimensional version. On the right-hand side, I have shown the three-dimensional version, but you get the idea. Okay, now you remember in the bottom, at least in this plot, in the bottom, I have few states. E1 could be 0, let's say, because it's the bottom. And as I'm going up in energy, E2 and E3, I have few more states. Now, it need not be like this anyway. For one-dimensional, you remember the E1 will have more states, E2 will have a fewer, E3 will have even fewer states. Now, these are the apartments in which the electrons have to live. So let's see how the electrons get distributed among themselves, among these states. Now, there are three rules that these electrons need to follow. The first one is only one electron per state. Now, including spin, but we will not talk about spin explicitly. For the time being, we'll ignore spin and we'll say one electron per state. So you cannot put two electrons in a box like that. That's first rule. And this is a rule anytime something has a spin of half integer spin, any particle, of course including electrons, that has this rule, that no two electrons can sit here. The next one is the total number of electrons are conserved. That no matter how you do it, you have 250 electrons in the beginning, you do a rearrangement, you cannot have 252 electrons at the end. Now, this may sound obvious, but for many particles, this is not the case. For example, for phonons, two phonons can essentially join into one, so the phonon number is not conserved. So there are many particles where the number is not conserved, and at least for the velocity that we are talking about, the energy that we are talking about, electron number will be conserved. And finally, the total energy of the system is conserved. Again, a non-trivial statement, but we'll assume this, because it's always possible for two electrons to come in and collide at such a high speed that a photon comes out. So two electrons comes in, two electrons goes out, but also a photon is coming out. So therefore, the energy of the resulting electrons is not necessarily conserved. But for this distribution, we'll assume that they are. Okay, so let's see how just based on these three rules, how we can derive Fermi Dirac statistics. Now, by the way, one thing on a quick historical note, many times we see Fermi Dirac statistics in solid state books so prominently, we always assume that this was derived for the solid. But remember, Fermi and Dirac both independently derived it, and they derived it before the band theory of solid, that there is a band gap, that there are these quantized states. All these things are derived around 1935 or so. After that, Wilson's paper that we will see posted on the website, in our website. So this is 1924, 1925. So therefore, at that time, there was no notion of a solid state and band diagram and others. So first few applications are really in the astrophysics area. It was later on transferred to solid state devices. And there is a very nice article at Wikipedia that you can take a look. Historically, this is a very interesting development. So let's take one example and go through slowly, because this is an important example. In the bottom, E equals 0 on the left-hand side, I have two states. At the second level, I have 5 and 4, and the energy equals 4, E equals 4. Now this, I don't show the units. It could be milli-electron volts, for example, some arbitrary unit here we are talking about. And this has a certain number of states there. And the total number of electrons, you can see, counting the red and the magenta one are 5. And do you see the total energy is 12, because 3 multiplied by 4 is 12 on the top side, the magenta one, nothing on the level 2, and the red, yes, I have 2, but they don't have any energy. So I have a total of 12. Now I always have to, no matter how I arrange, I have to make sure that those number equals 5 and energy equals 12, that are not violated, right? Those two I have to make sure that these are correct. But first of all, how many ways electrons, given this configuration, how many ways can the electron arrange themselves without changing levels, staying in the same level? Do you agree with that statement? What I have shown W is the number of configuration. 203, which is the subscript, says first level has 2, second level has 0, third level has 3. So take the first one. I have 2 states, factorial 2, divided by factorial 1 and factorial 2. 2 states, 2 electrons. So I actually have just one way of arranging it. Do you see that? That comes out the first factor. The second one is empty. So factorial 5, but then denominator has factorial of 0. And also a factorial of 5. Do you remember this formula? Right? This is simple arrangement of things within boxes. And again, I have certain number of states, no electrons. Well, I have just one way of arranging it. I cannot arrange vacuum in multiple ways. So I again have 1. But fortunately for the third level, I have drawn it incorrectly. I should have drawn another box because I write factorial 7. Third level should have seven boxes. That's a mistake. So factorial 7 and factorial 3 and 4. You get the idea, right? And that's 35 states. So that means within this, you see what might happen, that the 3 magenta one, all 3 could be pushed on the left side. That will be one configuration. The one shown here is another configuration. 35 in total for this case. What about slightly different way of arranging things? Remember, we are trying to say how the electrons are getting distributed in bands. That's the goal. And we are trying to see, we are allowing them every opportunity to distribute without violating the rules. The second one, do you agree that this again has 12? You should, because on the top, the third level, I have 8. Magenta one, 4 multiplied by 2. The blue one, 2 multiplied by 2 is 4. And then the third one is 0. So I have energy of 12. I still have 5 electrons in here. So I'm good. I'm good with these rules. And you see, no 2 boxes. No box has 2 electrons in it. I'm good with the first rule also. Again, you can quickly check 1, 2, 2, the configuration. Again, very quickly, you can see 420 levels in this case. It sort of makes sense, do you see? Because in the blue state, there are some configurations that you can have, and every configuration you have of the blue state, the other configurations get multiplied. So therefore, will be much more, you see. Is it the only one? Not really. There's another one that you can check. This one also has 4 blue, each having energy 2, gives you 8. 1 magenta gives you a 4, 12. 5 electrons still, the bottom level is unoccupied, no red. Again, how many states? Again, we can calculate 35. Now, the first one and third one being 35 is just accidental, you can see. In general, this need not be the case. Now, if you didn't know any other physics, which is the most probable configuration? That if you came in and did measurements, at different times? Most likely, you are going to get the 1-2-2 configuration, right? Because out of 420 plus 70, out of 510 measurements that you can do, in 420 cases, you'll find the electrons distributed according to 2. Most probable distribution. Fermi Dirac statistics is most probable distribution. This is not the only distribution. This is the most probable distribution. You see, even in 3 states, the one level is most probable is 420, about a factor of 10 or more higher probable than the other one. If you had a few more states, you can very quickly see the most probable states will be orders of magnitude higher than anything else you can have, right? So that is what this middle one will result in Fermi Dirac statistics. See. So let's plot it. That's the point I wanted to make. So the most probable state is 1, 2, 2, and that is where we'll have our Fermi Dirac statistics. Now, in general, I have here 3. I could quickly calculate which one is the most probable. But if you had 50 of these states, how would you calculate the most probable? Well, the way to do that, you will take W and take a derivative with respect to the configuration. You see, going from 202 to 122. And at the point where it's maximum, the derivative will be 0. You see, I changed the particle a little bit, number of configuration a little bit, number of configurations goes down quite a bit. Then I know that I'm at the maximum point. So that is something we are going to think about, use it in a few seconds. But for now, I already know that answer. What is the maximum? 1, 2, 2, and let's go with that one. So this is the most probable distribution, and from this most probable distribution, I can calculate what is the most probable occupation per energy. For example, you see, in the most probable distribution, I had 1 in the red out of 2 states. So my probability at that energy that something is occupied, that I find an electron, is half, right? 1 divided by 2. In the second one, you see 2 divided by 5. 2 blue electrons, 5 states. So on the average, I will find 2 over 5. And the third one, 2 over 7. You get the idea. Now, do you also get the idea that as you are going up in energy, the probability of occupation is actually going down? You see, that is for going down. And F of E, this F is the Fermi distribution, because it tells me how electrons are distributed as a function of energy. So the red one here on the top will be half, 2/5 is the blue one, and the magenta is 2/7, and that gives me, let me quickly, and that distribution essentially will tell me how they are distributed in energy. Now, I'm now going to go to big solids. But before I do, let me quickly point out, you know that transistors are getting smaller, right? Many people say that there will be a molecular electronics. By that, they mean that the device would be so small that a single molecule or a collection of molecules will be able to turn the transistors on and off. In that case, you see, the derivation I'm going to do now, that is less applicable than the type of derivation I just did, because this counts finite number of states very precisely without making any assumption about large number of states and large number of electrons. It doesn't make those assumptions. This is an exact calculation. So sometimes you may have to be able to do that, especially for the devices that you might handle during your research career. But to go back to the book, it's a historical derivation where they had a lot of electrons. Remember, 1 centimeter cube, how many atoms do you have? You have on the order of maybe 10 to the power 22, 10 to the power 23 atoms. Huge number of electrons, huge number of states. So in that case, we can take some more approximation. So for n states, generally, what you will do is calculate it if Si is the number of state at energy E, I stands for E here, because I is various levels, energy levels. I stands for E. And do you see why it should be S factorial divided by S minus N factorial? N is the number of particles. It is exactly this formula. You see, when the C, W sub C, the C means configuration. And the configuration is 203 is a configuration. And just like I multiplied here various configuration, I am doing exactly the same. You can see the multiplication symbol over I. So exactly the same step. Now, of course, when the numbers are very large, then I can do some extra things. I can take a log on both sides. I'm missing a C below subscript on W, but you get the idea. And you also get the idea that when multiplication under log, it becomes a sum. Do you see a sum? And then you can see how the logarithmic has been spread out. Now, at this point, it is logarithmic of a factorial. And we know the Starling formula is given by this. Si ln Si minus Si, you can see just the first term gets expanded like this. This is actually pretty good formula in terms of approximation. Anytime you have S larger than 10, this is a very good approximation. So, if you have that, now do you see all the linear term in Si, that will disappear? See the red Si and with a minus sign, and towards in the middle, you have a plus Si, but that's a red with a red one also. So that will cancel. Similarly, the blue one will cancel, and that will eventually going to give me a simple formula like this. Now, what do you say? The first term is actually a constant, right? Do you see? First term is constant. The last term, second and the third term depends on number of electrons. So you can immediately see when I take a derivative of W, I want to know the most probable one, remember. Then the first term will drop out immediately, you can see. Okay, let's try that. So this is what I'm doing. You see, I'm taking a derivative. Why? Because I want the red one. And I have many states, so I cannot just go and look at each one of them individually. So I look at those separately. Now this one, just from the previous step, if you take a derivative, you will get the first term within the bracket. Now I'll ask you to check it out. You know, this is one step. What you will not get is the second and the third step, third term with the alpha and beta there. But you can see what alpha and beta does. It says that if I change the total number of electrons, redistribute them a little bit among different levels, right? What should be the sum over delta I? It should be 0. Why should it be 0? Because sometimes I take 2 electrons from one level, bring it to a different level. So from one level's perspective, this is minus 2. From a other's level perspective, it is plus 2. So when I sum them, right, therefore all changes, because electrons cannot be created or destroyed. So therefore, in this case, sum of delta Ni, that should be 0. And when you want to introduce that constraint, this is something called a Lagrange multiplier. You introduce it in this particular way. I'll post a very nice note in which you will see how the Lagrange multiplier is a simple differential equation concept, and not differential calculus concept. So you will see how it goes through. And the beta similarly says that the total energy must be conserved, right? While you are rearranging the configuration, you cannot take any configuration. Only the subset that keeps the total number of electrons the same and the total number of total amount of energy the same. So only those are allowed. And once you do that, you can see there is a delta Ni in every one of them, and so you pull them inside. And again, that's the most probable configuration. Now the whole thing has to be at the maximum point. The whole thing has to be 0. Now if the whole thing has to be 0 regardless of dni, then the term inside the square bracket must have to be 0. So if that is 0, do you see that you can immediately transfer it down to the next equation? How do I do that? You can see alpha and beta, I can take it to the right hand side, it's a log, I can make it an exponential. And remember, in the first equation I have SI over NI, and I define F as the number of electrons in a number of states, right? And so therefore I have flipped it. So you can see how the 1 over exponential term might come about. Okay, so now from here you can see that I can calculate this number. What are the, if I knew alpha and beta, somehow if somebody told me alpha and beta, I'm set. How do I calculate alpha and beta? The first is, I'll assume something, the first one. What I will assume, again, this is that Fermi energy, EF, again it will come later on, the physical meaning of it. But for the time being, I will say that if there is a state, the Fermi level, then the probability of occupation of that level is half. I'm just defining it. I could say probability of occupation is 3/4, whatever I want. So I am defining it, Fermi level, to be that energy in which it is occupied at a level of half. So, by the way, do you see that regardless of what you do with energy E, you cannot make it more than 1 in this particular case. So 1 over the exponential. So regardless of this, the maximum point here for Fe will always be equal to 1. Now at F equals EF, probability of occupation is half. And so therefore, do you see that if it has to be half, then the top of the exponential, alpha plus beta E, must be 0. Do you see that? Because e to the power 0 is 1, and 1 divided by 1 plus 1, that's half. So this must be the condition, and that relates alpha and beta. The second condition is that so you can get an expression for alpha equals minus beta F and insert it in there. The second condition is that at very high energy, 20 eV up, the probability that any electron will be occupied is 0, because that high an energy nobody has. As a result, at E equals infinity, infinity means maybe 3 eV, 4 eV, whatever, and in that case it must be given by the Boltzmann equation, Boltzmann relationship. And by comparing these two, do you see what the value of beta should be? When E equals infinity, then E equals plus infinity. That means it's much, much greater than EF. So beta E will become a large number compared to 1. So I can drop 1. And so it becomes e to the power minus beta E, right? And e to the power beta E, so it can be compared with Boltzmann distribution, and as a result beta is 1 over kT. So beta is related to the temperature. Does it make sense? That as you raise temperature, in fact, this distribution will get broadened out. Higher levels will be occupied. So therefore you have 1 over beta kT. Okay. Now I know this is a little complicated derivation. You have to do it once, so that you can torture your students with this type of derivation when you become a professor. So, but for the time being, let's stay with that. Oh, by the way, do you remember from the discussion before where we had just 3 levels? So the first level has probability of half, right? Do you remember? E equals 0, half, 2/5, 2/7. So that level was actually the Fermi level in that case, because that had a probability of half. Okay, that's it. So I know this is the distribution for electrons in any given energy E. If I know somehow, if somebody tells me EF and the temperature, I'm all set. Temperature I know, my computer is working in this room, whatever is the room temperature, that's my T, but somebody has to tell me what EF is. That will come later on. This is one derivation, 2 more to go. The other derivation is something like this. So let me step back. You see, how did the electrons, let me step back. how did the electrons, I said 3 configurations, remember, in that one? But how did they go from one to another? Actually, what is happening inside, let's say the magenta one scatters with the blue, and as a result, the magenta goes down. Magenta scatters with the red has energy 0, and magenta has energy 4. They scatter with each other, and then they both go to the blue states, because the bottom one got an energy of 2, the second one got an energy of -2. So the energy is conserved, right? And similarly, electron number is conserved. Actually, just from this statement, you can calculate the Fermi Dirac statistics in one sentence, one slide. Because this process, if the electrons, the blue and red and magenta can create blue electrons, similarly, 2 blue electrons could scatter, and they could go to the magenta and the red states, right? They can go back and forth. This is called detailed balance. We'll use it a little bit later. That anytime there is a scattering that allows electrons to go to some states, the reverse process must also be allowed and must have the same rate. So do you see that F naught at E1 being, let's say, E equals 0, when it scatters with an electron with an energy E2 being the top level, and F3 and F4, where the electrons are F3 and E4 and E3 are the places where the electrons eventually go. So those will be the blue states. The blue states must be empty. Remember that a state cannot be filled by 2 electrons. So if they are not empty, you cannot go there. So the first level says that how the magenta scatters with the red and goes to the blue. And the blue must be empty. Therefore, I have 1 minus F naught, 2 factors of 1 minus F naught on the first term. Now remember, the reverse process must also be permitted. So therefore, the E3 and E4, those are the 2 blue electrons. If they scatter, they must be able to go to the magenta states with 1 minus F naught at E1 and 1 minus F naught at E2. Okay? That's it. My derivation is done. Because if I further require that E1 plus E2 must be equal to E3 plus E4, because energy has to be conserved, you see, then the only solution to this equation is this. That's it. No complicated derivatives and others. Actually, Fermi Dirac statistics is this powerful and this simple. This is the only way configuration of electrons within states are possible, you see. Okay. Now this we will be using it quite a bit towards as the semester progresses. Okay, now let's do the third one that we'll be also using quite a bit. Now something called derivation by partition function. Here we'll assume something and then I'll give you an example to show how it works out. So this is called a partition function. Where I got it? I opened my statistical mechanics book. If you take a course, statistical mechanics, you will get a formula like this. That probability that a site energy of level I is occupied is given by this complicated formula. I'll show you an example to show how it works. We'll not derive it. Do you see that EI and NI floating around in the numerator? So that's the energy of the electron at that level. Ni is the number of electrons in the level. I'll show you an example how it works. And the denominator, instead of carrying it around because it's same for everybody, I'll just call it Z and not write it over and over again. Okay. Let's say I just take one stage. Did you see it in a very nice animation I see here? So it went down. I'm just focusing on one state. And this one, the PI, tells me any state I, how it's filled. So how can it be filled? Either it can be full or it can be empty. You see, one level, one electron, it can either be full or it can be empty. All the energy conservation, particle conservation, all built into the partition function. I don't have to worry about that anymore. So I'll just have to worry about the configurations. Okay, so if this is the case, then say that there are two possibilities. If the level is empty, which is the top line, we'll call that state 0. No electrons in that box. If there's no electron, how much energy do I have? Well, nothing. You can see EI is 0 also. No electrons, well, Ni is 0. And if I insert it in my partition function, you will see I'll put EI equals 0, Ni equals 0. So the numerator is e to the power 0, and that's 1. So the formula Pi for state being 0 is 1 over Z. You see that? Now what about states being occupied? That's the second line. State being occupied, I call that 1. And I have EI, I have 1 electron. So I have EI equals EI, yes, that's the energy. Ni, well, 1 electron. Ni is 1. I put it in, and that's my formula. Okay, I'm done actually. Because the probability that a state is filled is sometimes it's full, sometimes it is not. What is the probability? Well, the probability is this. Sometimes if it is full, then it's P1. Sometimes it's not, it's P0. Put that formula in, from the table, and that's my Fermi Dirac statistics. Do you see that? That's it. You see, this will be necessary a little bit later again, because without doing some tricks like this, doing more complicated derivation is very difficult. I can skip all those to make your life easy, but you need to know. These days devices are getting so small, you actually need to know this. Okay, so you have seen 3 ways of deriving Fermi Dirac statistics. So you see, general property is that when energy is very small, then the maximum is 1. When it's very large, it goes to 0. And somewhere in between, at Fermi level of EF, there's a half. And many times I'll be drawing it this way. The same equation rotated 90 degrees. Fe plotted in the x direction and energy E in the y direction, and EF is somewhere in between. Okay, very good. So a few quick comments. So as I said, it applies to all spin half particles. The information about spin is not explicit. Many times we'll just do all the calculation and multiply the end result by a factor of 2. But this is not true for many magnetic materials. People talk about spintronic transistors and other things you may have heard, and you have to be more careful on those when you distribute particles. And the most interesting part is, and this I want to emphasize, that the Coulomb interaction among the particles is neglected. I pushed 4 electrons over there sitting next to each other. Now the electrons don't like each other, right? Strong Coulomb interaction. How is it I allowed them just sit in the neighboring boxes and nobody is complaining? This is because this theory actually just applies to solids, of long solids. You cannot really apply it to small molecules, because then there is something called a Coulomb blockade. That's a different thing. But this should have bothered you a long time. I'm sure you have seen this derivation many times. Why is it that electrons don't really repel each other here, and why didn't I include that factor in? This is why. Because if you take a solid of length L, 5 million atoms, then these are the energy levels. The dotteds are spin up, and let's say the solid is spin down. You have a bunch of states. The reason it works, because the electrons, although they are at the same energy, they are actually far apart. They don't see each other. Because if they did, there would have been Coulomb interaction. So it is like you have 1 electron, then you have an atom with its own electron, another atom with its own electron, a million of them, then another electron sitting on the other side. So therefore, they don't see each other. Therefore, I didn't include the Coulomb interaction term here. You see, it's very important. So therefore, when you take a molecule, your professor asks you to do a calculation, you're happy, Fermi Dirac statistics, put the numbers in, your result will be wrong. So be careful where you use it. It's a powerful but dangerous tool. Okay, I'll take 10 more minutes to get started finally on something useful. But before that, let's think about what we have learned. Density of state. That density of state only applies for 3D, but you get the idea. And I'm just drawing the conduction and valence band. Always remember that there are lots of bands underneath and above this. This is for silicon and germanium 3s and 3p states. That's what I'm sort of drawing. I just learned about Fermi Dirac statistics for the electrons with a certain given EF. Now you can see if I move the EF up and down, the whole curve will move up and down. Okay, fine. I'll see how to fix that one. And do you see that if I multiply the density of state, how many apartments? Fermi Dirac statistics, probability an apartment being occupied, multiply them to, then energy by energy, I can get the number of electrons. That's shown here on the red on the right hand side. In the middle, I have nothing, because although Fermi Dirac probability of that site being occupied is not 0, right? But there's no states. And if there's no states, when I multiply, I do not get any electrons or holes on the right hand side. Now that's about conduction band electrons. What about the number of holes? Okay, so if I wanted to calculate the total number, I will start with EC on the bottom and E top, whatever is the end of that band. Remember, all bands are finite. Whatever is the top of that band, multiply them energy by energy, sum it up, I get my electron number. What about number of holes? Well, holes is anytime there is no electron. So if the probability of occupation of a state is F, what is the probability that I will find a hole? 1 minus F. And 1 minus F is a blue line. And again, if I wanted to calculate how many holes, I will multiply the blue density of state with the blue Fermi Dirac, 1 minus the Fermi Dirac, and that will give me the number of holes. And the number of holes, again, I can easily calculate, integrate it over, I get total number of holes, right? This is it, general prescription for calculating the any electron distribution. Now you see, only thing unknown in here is the EF, because I know the density of state. As soon as I know a material, I know the effective masses, right? I know the effective masses, the band gap where EC and EV are. I know all those. Only thing unknown, somehow if I could get EF, I'm all set. I can calculate N, I can calculate T, and I can calculate conduction. So let me do that. I'm again doing it for 3-dimensional solid. In exams, sometimes I give one same derivation, but I may ask you to do it for 2-dimensional solid. In that case, you see, the G sub C, we will change it with a different formula, right? But other than that, you will do the same derivation in here. By the way, there is a 2 multiplication explicit, because so far I had been talking about density of state without spin. If you wanted to include spin, then I put that 2 multiplication just to take care of the spin. Now the E top, I'm setting it to infinity. Do you see why? Because the Fermi Dirac statistics actually decays very fast. And within a few kT, kT is 25 millielectron volts in room temperature, band width is several eV. So millielectron volts and several eV on an exponential. So therefore 4 eV is as if it is infinity. So I replace the top integral with infinity. If the band is very narrow, don't do this, because remember some of the bands towards the bottom were very narrow. In that case, the width of the band may be actually equal to few kT. If you do this, you'll get completely wrong result. So be careful. Now all I have done going from these 2 states is have rewritten the Fermi function using a variable E minus EC, but apart from that, and call that eta C. Is that the right? Or need? Okay. And therefore, I can calculate this whole thing, and I can just rewrite it in 2 forms. One is N sub C. Now you see capital N sub C, and another is this Fermi Dirac integral of order half. This is the capital F. Why it's half? Because you can see that there is a square root sign here. So therefore, that is why it's called half. If it had a 3/2 sign, then it will be called 3/2, order 3/2. For the time being, let's say that this is my derivation. What does it mean? What does it mean? I just write it this way, but what does it mean? This is what it means. So before I go there, what it means, I just want to point out that if you plotted the function, the exact result with Fermi Dirac integral of half, or an approximation which is nc e to the power eta c, if you did that, that is the plot on the right hand side. That's the plot on the right hand side. And you can see for the most electrons, and I'll show that later on with examples, I'll show that later on, that if the energy level, the Fermi level, is few kT below the conduction band. Remember the conduction band and the Fermi level is somewhere in between. If it is few kT below, then the simpler expression eta c, nc over e to the power eta c, that's sufficient. I don't have to do that complicated expression. So this is what it means. Forget about all the derivation. This is what what it actually means. You see, my electrons are actually distributed in energy, right? You see that? The red one and the holes are distributed in energy. Instead of thinking about these things as being distributed, I can do the following. I say, I don't have like apartment buildings going from here all the way to the top. I will compress all the apartments into one level at EC, compress them all. Now that is what will be called an effective density of state. Because I had it all spread out in energy, I've squished it all at energy level EC. And that's what will be called it's in sum over all the states, and that's called an effective density of state, NC, effective density of state for the valence band, NV. And I will just think that I don't have this distribution, but just I have one level, and that level occupied by the Fermi factor. That's it. I will not have to do this integral over and over again, because I have effectively compressed the information into that level, and just one level how it is occupied. Now this is very important. This distinction is very important to understand, because effective density of state is not density of state. Density of state is energy resolved. Effective density of state is an integral. So therefore, this have to be, you have to understand this. Okay, so let's talk about electron and hole. I have maybe two slides. So let's say I have this n equals that expression, nc e to the power beta ec minus ef, right? So nc is that effective density of state, and you can see that exponential factor is the probability that that state is occupied, right? That's the Fermi Dirac, approximate Fermi Dirac factor. And correspondingly for the holes P, I have NV, effective density of state sitting in the valence band. And again, the probability that a hole is found. You can see the change in sign. One case a minus, another case a plus, because one place it says occupied by electrons, another case it says not occupied by the electrons. Okay. Now, if I multiply, that gives me a very strange relationship. Because when I multiply n with p, you can immediately see that the EF disappears. You see that? Because in one case I have plus EF, another case I have minus EF. EF disappears. This product, do you see, is independent of anything of the material. And so long I know the material, I know NC, I know NV, and do I know the band gap? Of course. Chronic Penny model, I solved the Schrodinger equation, I know it. And beta, well, beta is 1 over kT, as I know temperature. So the amazing thing is, regardless of what you do for the solid, however the electrons move around, this doesn't care. This product is one relationship you will use throughout the semester, and this will give you a lot of information. So finally, let me end with this. that if I have a solid in which it is intrinsic, means a certain number of, let me see whether I have, okay, I may have it later on, but let me see. So let's say I have a solid, I raise the temperature. It was at 0, raise the temperature. Some of the electrons which are in the valence band now have jumped to the conduction band because it's more energy. So the number of electrons that I have is equal to the number of holes I have, because where will the holes come from? They are coming from because some of them have gone elsewhere on the conduction band. So for intrinsic semiconductor, I have N equals P, and I'll call that Ni, I for intrinsic. Now, do you remember in the last slide, N multiplied by P is always that relationship, Nc Nv to the power? You know that, right? So here N is equal to P. So you have Ni squared. So you see now from beginning to calculate the number of electrons that can take part in the conduction, because that's the number of free electrons in a partially filled band, Ni, and that's also the number of holes in a partially empty band, and that's also Ni. So I can easily calculate it. Where is the Fermi level? Well, if N is equal to P is equal to Ni, I can immediately solve for it. I know the band gap Eg, I know Nc and Nv, I know beta, and if Nc is equal to Nv, then where is the Fermi level? Nc is equal to Nv, therefore that's 1. Log of 1 is 0, and therefore right in the middle. If Nc is equal to Nv, right in the middle. If Nv is significantly larger than Nc, then what will happen? Nv is large. I have lots of density of states on the bottom side and a few apartments on the top side, few, right? Nc is small. Then Ei will be above this. Do you know why? Do you understand why? It is because unless the Fermi level is close to the conduction band, they have only a few states. So their occupation has to be much higher in order that the number of states multiplied by their occupation becomes a number comparable to the valence band number. And as a result, this value of Ei, you should convince yourself that this formula is physically correct. Otherwise, in the exam, what you will do, many times this formula will get flipped around depending on what you remember from your memory. But rather, it's good to do it physically. Okay, so let me conclude here. So we have discussed Fermi Dirac statistics defined by the states, occupation statistics defined by the states from the solution of the Schrodinger equation. From now, we will not talk about Schrodinger equation anymore, because all the information about Schrodinger equation, everything is hiding in the effective mass, right? You see, for every band, the effective mass is different. That is where all the EK relationship, the curvature, the bottom of the band, quantum mechanics is hiding in the effective mass. We'll not think about that anymore. That's where it goes into density of state. So density of state hides the quantum mechanics, all the chronic penny model, everything. We'll not also talk about Fermi Dirac statistics explicitly anymore. All information about Fermi Dirac statistics is hiding in EF and the temperature T, because you have seen the relationship. We'll multiply, we have found a new relationship, N multiplied by P, independent of how you fill the states, how many states you have, right? Nc, Nv to the power of the band gap. So these three things we have learned in this class, and then rest of the semester, we'll be just applying this over and over again, and you'll see all devices, your MOSFET, your bipolar transistor, this laser pointer, the physics of all of those will gradually just flow out of these very simple concepts, right? Thanks.